start now by repeating or showing something related to what I explained yesterday about LP. And suppose we are equipped the space with the two norms that I introduced. Suppose I equip it with these two norms. You must still remember the formula. So x here, xj, xk, yj, yk taken to the power p, and then you raise it again to the power of 1. And I mentioned that if we take a set of two linearly independent vectors, then I can define the star node. Yeah, but for simplicity, I will give an example where the set of two linearly independent sets are consists of E1 and E2. So E1 is just 1, 0, 0, and then E2 is just 0, 1, 0. Okay, so I can define this as algebraic summation because it's only two terms plus but what will this formula give us? So that's what I'm going to do. So remember, if x is, this is just an illustration, and e is 1, 0, 0, 0. How to compute this, or this formula? You take any two columns, and then you compute the determinant. Okay? Why do we have a half? Because from the two columns you can have two combinations. So that's because here j and k goes from 1 to infinity. If you don't want a half there, you can choose k and then j greater than k, for example. Then you don't need a half. But so here, for example, if you take this column and that column and you compute the determinant, you get x3. You get x3. Oh, I need an absolute value. Okay, absolute value. Okay. So you get x3 minus x3 actually, but then you take the absolute value. And if you do that, you get everything except x1. You get everything except x1. So you get this to the power of p, that to the power of p, x mod of x4 to the power of p, and so on. So, and of course each has two possibilities, but you multiply it by half, so you get this. So this will be the value of the two norms between x and e1, raise it to the power of p. Okay? Now, sorry, this is e1. If you do the same with e2, then you get everything except the absolute value of x2. Okay? So when you compute this, then the norm of x star is 1 P with coefficient 1, mod x2 to P with coefficient 1 also, and everything else with coefficient 2. Okay? So j greater than 2. And all this is raised to the power. So that is the norm that we have. That's why you can see clearly that this norm is equivalent to the original norm with constant 1 on the left and constant 2 to the power of 1 over p on the right. Okay? So that is just a simple example that might give you some concrete ideas about the star norm. Today I will begin with today I will talk about orthogonality also, like Eder, but in n-norm spaces. Actually, to be more precise, I think I will talk more in an inner product spaces. Okay, so I'm not going to use the functional G, but actually, what I will talk now was a joint work with Eder, like 20 years ago.
14 years ago.
No, maybe 12 years ago, because you were finishing your undergraduate study at ITB at that time. Always. I said I was lucky because Eder has explained this, so we didn't talk to each other before we gave our lecture, right? So the order is just right. Okay, so we know these notions already, so I can skip this slide. Okay, PI because sometimes it's called also because of James, right?
I think it's James because for the alpha it's complex.
Oh, okay. So if alpha is real, then it's beta. Okay. Now, if X is equipped with an inner product, then of course Eder also has mentioned this, right? That the three orthogonalities are all equivalent to the usual orthogonality. However, in a known space, which is not an inner product space, one does not imply another. You can check this book if you're lucky. Oh, not this paper if you're lucky. I don't know, it's an old paper, but maybe it's online now. Yeah, in the year 2000 something, we learned that many researchers have extended these notions of orthogonality to two norm spaces. For example, the works of Cho and Kim, 1983, and also Han and C.P., 1982. As the notions of orthogonality in norm spaces are inspired by the notion of orthogonality in inner product spaces, so the notions of orthogonality into norm spaces are also connected to that into inner product spaces. So I will focus more on the notion of orthogonality in two inner product spaces, and then later on in n inner product spaces. Okay. So me with my showed that Cho and Kim's definition of orthogonality into inner product spaces are void. What's that mean? What does that mean? That means you cannot find two vectors that satisfy the condition except one of them is 0. If one of them is 0, then you are talking about nothing. So, the reason is that they require a condition too strong, so strong that no pair of vectors can be orthogonal. But they didn't realize that. And condensativity's condition is too weak. So weak that every pair of vectors will be orthogonal. Of course, then it's too ridiculous, right? To have every pair of vectors orthogonal, including pairs of dependent vectors. Why they miss this? They miss one thing. They treated in two inner products, remember x, y, and then there's z. They treated z just like parameters. Z plays an important role in this case. As I've shown you yesterday, the problem of finding the right set for Z is very important in this business. So I call the set of testing vectors. And for the orthogonality, this business is a bit tricky. You don't want to have too many, but you don't want to have too few also. You have to have the right number of testing vectors. That is the key. So imagine, I'll draw a picture here. You know, these are orthogonal, right? Okay, my picture maybe not here. But that's in two space. So now, if we are in a three space, we have another set. Okay. Now, the role of this set is that if I have one vector z, that means we are computing the angle between two planes. Okay? So, for example, if this is my z, then I have this plane and that plane. Okay? So, choosing this z, I get an angle which is not 90 degrees. So, but choosing this z, I get this plane and this plane and that plane are orthogonal. So, I get at least one z that makes the angle really orthogonal in the usual sense. What that means is that if I actually work on an inner product space, then my definition should coincide with the usual one. Okay. So we then offer the standard definition of orthogonality in the inner product space for the dimension where the dimension is greater than or equal to 3. Again, I'm lucky because Eder has mentioned for two-dimensional is another story. Also, yeah. But then later I will talk orthogonality in n-normed spaces. So I will assume that the dimension is n plus 1. For the n dimension, another story. Why is that? It's clear. If we are in two-dimension space, I cannot have z sticking out of the whiteboard. Okay? So z should be on this space also. And what is the angle? The angle, the angle is 0 all the time. So I have to create another or a different definition. Okay, we'll talk about that later. So we define G orthogonality. Again, this G doesn't have anything to do with my name. They call it G before I work on this, right? So we define G orthogonality into known spaces as follows. So G is orthogonal to Y, denoted by this Eder is small letter G, this is capital letter. If and only if there exists a subspace V of codimension 1. This is what we found. The right size of the set of testing vectors is one dimension less than the dimension of the space, such that this the value of these two inner products is 0 for all z. So I didn't tell you how Cho and Kim defined it, or Khan and Shiki, but Cho and Kim requires that this holds for all z not in the span of x and y. So that is exactly like this. So you can choose z anything, and then there should be 0. Okay? That's too much. Okay? And Khan and Siddiqui, on the other hand, require only there is a z in blah blah blah. So there is. So they use existential quantum, while Cho and Kim use universal quantum. One is too much, one is too few. So we look for what is the right size of the set, and we found that that this should only hold for z in a subspace having coordination 1. Of course, we have to prove that with this condition, in the case where X is actually an inner product, and the two inner product here is the standard two inner product, then this condition coincides with the usual conditions. Okay? But I will do that in the general setting, meaning I will show that in n known spaces. So, but if you then work in two known spaces without two inner products, then from the previous definition, we could define P orthogonality I, and then the orthogonality like this with the same size of testing vectors. Okay, not for all z, but for every z in V, where V is a subspace of. And this is existential quantum. So there is a V. So we must choose V actually. So now I will talk about this in the setting of n known spaces. Okay? So I haven't mentioned this earlier, but you can guess that in an n inner product space, which is also equipped with the induced n known, we have the parallelogram law, and we also have the polarization download, you have learned from book and also reminded by Professor Kato, is a characterization of, in this case, of an inner product space. Okay. So this is what Choi and Kim definition, what Choi and Kim's definition of G-orthogonality. So they define that X and Y are orthogonal if the value of this n in the product is 0 for all, in this case x2 up to xn, not in the span of x and y. So that's your x and y, and the other just outside of the plane. Okay? And not only Choi and Kim, Godini, I refer to Godini here as his review in the MYSAGA. He also strengthened this, made a statement about the condition, confirmed the condition, but actually, after we, this is what happened really. So my feeling at that time, this cannot be right. This cannot be right. This is too strong. First of all, this is not a space. The complement of this is not a space, right? So so we were thinking, and then we found the result. First of all, we showed that if this is satisfied, this condition is satisfied, then x or y must be 0. So, meaning that their definition, I call it void because you don't want to talk orthogonality about 0 vectors. If one of them is 0, then what is the use of orthogonality? Okay? So, how do we prove this? I will give you the file. Okay, so I will not explain line by line, and I'm not like Eder have the energy to write down the proof. So, but this is what she actually did a couple of years ago. Do you remember this? Yeah, the note actually was is unpublished, so we don't send it to any journal. But with this, I think you apply for the position in Australia, and Mustafa Dragomir accept you, right? Yeah. So suppose x and y are not 0 vectors. So our task is to show that there exists x2 up to xn not in the span of x and y such that this is not 0. If we can do that, then the contraposition holds, right? So to do so, we consider several cases. First, if x and y are linearly dependent, so that is, I think, easy, because you can assume that y is equal to a multiple of x, and in that case we have this relation, and you just choose x2 up to xn not in the span of x, such that this set is linearly independent, and we have enough space to choose n-1 vectors other than x, so that this set is linearly independent. Okay, and that will give us the value of this. If y is a multiple of x, so So you take out k, so and here we have x and x, and this will become n norm of x to up to xn square to the power of 2. So this is non-zero. So what happens if x and y are linearly independent? This is the hard part, but we could divide it into two sub cases. First is the case where the inner product is not zero. Remember, here we are in actually also even if we have an inner product, we are also equipped with inner product. So suppose they are not, this is not zero, then we may choose an orthonormal sequence. Now we use the assumption that the space has dimension at least n plus 1, okay? N plus 1. So we still have at least n minus 1 vectors that will make altogether, well, not altogether, but the orthogonal projection of x and y is we can choose an orthogonal sequence x to up to xn. So using the formula for the n inner product, remember the formula of the n inner product. Now I will write down there. X2 up to xn is xy here, and then x2 xn, and here x2 y, so here xn y, so y is in the first column and x in the first row, and everything else here is just x2 up to xn. xn, x2, xn, xn. So by choosing x2 up to xn or normal to x and y, so these guys are 0 and these guys are 0 too. So the determinant is just the inner product of x and y, and we know the determinant of this is the norm of n norm of x2 up to xn, but they are also orthonormal, so we know, yeah. Okay, and this is not zero. So what happens if x, the inner product of x and y is 0? What happens if they are orthogonal? Well, in that case, we can choose non-zero vector x2, which is equal to x plus y plus, so x plus y is this, x plus y, and then add u, so add u so that it's sticking out of the space, so we have a vector not in the span of x and y, perpendicular to x and y, so add this, okay? And then non-zero vectors x3 up to xn, not in the span of x and y. X3 is also perpendicular to the span of x and y, and so on. So that is to make the computation of this determinant easy, of course. So we get this determinant, and everything here is 0. There is 0 also. We don't know what x, the inner product of x and x2, and also x2 and y, but from this we get if you think of this determinant of this, you get that, and then the determinant of the submatrix. So we get what we want. Okay. Thus, in any case, we can always find factors x2 up to xn, not in the span of x and y, such that this is not zero. We are done. Okay, so the condition imposed by Choi and Kim is too strong, and they didn't realize that. So as in two inner product spaces and two null spaces, we can also divide the I and the orthogonalities in null spaces as follows in the next slide. And for the rest of this section, I assume that the dimension is still n plus 1 or higher. So this is the G orthogonality, the same as in the two inner product space. We still have the analog condition, that is the existence of a subspace V of codimension 1, such that this condition holds for every x2 up to xn in V. Okay, and of course we still have to prove that this condition coincides with the usual condition in inner product space. And for Pi and Bj, B orthogonalities, I can skip them. Okay, so this is what we prove. We can prove that the orthogonality satisfies what properties is non-degeneracy and symmetry. We have symmetry here, yeah, and this is homogeneity. Okay, not all properties. Maybe we can check the continuity also, but I don't show or I don't write all of them here. The others exercise. So I don't also prove everything here. I just give an example here to prove the only if part of A, meaning if you have this, then x must be 0. To prove that, we suppose that x is G orthogonal to itself, and x is not equal to 0, so we prove by contradiction. Then the x is a subspace V of x with codimension 1, such that here x and y are the same, so we compute the n inner product of x, and then x2 up to xn here, and that is the n norm of x2 up to xn squared, and that thing is equal to 0 for every x2 up to xn in V. But since V has dimension greater than or equal to n, it's actually greater than or equal to n plus 1, so it must be greater than or equal to n. We can choose x2 up to xn such that these are linearly independent, right? So for those vectors, this must be positive. So on one hand, this is 0 for every choice of x2 up to xn, but on the other hand, we can can have certain x2 up to xn, which makes this positive, so it's a contradiction. Okay? So the proof is not computation like Eder showed, but here more logical consequences of the definition, condition, and the fact that the space has at least n linearly independent vectors. Actually, the space can have n plus 1. We don't need that much. And this part I think it's easy, that's an exercise. You don't see it. Okay. Yeah. So I'll spend 56 minutes. So the next theorem, I usually have next and below. So the next theorem states that in a standard and in a product, where the formula for the n in the product is given by the determinant, G orthogonality is equivalent to this. This is the important part of our result, because we don't want to define orthogonality in such a way that when we compare it to the inner product case, we get something different. Of course, there are notions of equivalence between even between angles and between norms, but orthogonal is orthogonal. So I mean, you don't want to alter that. So. Okay. So this theorem says that x is G orthogonal to y if and only if x is orthogonal to y in the usual sense when x implicitly by the word standard, meaning that x is actually equipped with an inner product, and the inner product is generated from the inner product by this, using this, through this formula. Okay? So, I don't have time, I guess, but let's see how we prove the necessary condition. So suppose that we have the usual orthogonality, so from right to left, that's what we are going to prove. That is the inner product is 0, and that x and y are not zero vectors. Then we can choose V to be the orthogonal complement of X. This means that V is a subspace of X with dimension 1, because X generates span X which has dimension 1. So the orthogonal complement is of codimension 1. Now, for every x2, x3 up to xn in V, we have this is 0. Why? Well, everything is orthogonal to x, so these are 0, and that guy is also 0. So the first row is 0. Okay? So if the first row is 0, then the determinant is 0. So that's okay. Yeah, I think for the sufficient condition, it's too long. Not that long. That's the end. But maybe you cannot grasp this quickly. But let's see. I don't think 40 minutes already. Yeah, spent 40 minutes already, so I'll just skip this. Okay. So what happens in the n-dimensional Oh no, that means I have to finish. So, okay, what happens in the n-dimensional space? Suppose we are in two-dimensional space. Then I don't have the testing vectors except vectors in that space also. And remember the two-inner product is the angle between the parallelogram spanned by x and z and the parallelogram spanned by y and z. So but if everything's here, then the parallelogram coincides. So the angle is 0 or 180 degrees. Right? Okay? So I cannot have 90 degrees. So we have to use a different definition, of course. Now the key is that in two known spaces, or even if we are in two inner product spaces, we can have a known or an inner product. Remember this formula. The same also true for two inner product spaces. If we are starting with two inner product space, we can generate an inner product. So we can use that instead. Why don't we do it? Well, first of all, the motivation is to correct jointing definition and also condensity. We can also, from the beginning, define an inner product or an unknown, and then use that to define orthogonality. But then maybe we don't have the identical definition with the usual definition. This example shows that the norm is not identical with the original norm. So if I define inner product from two inner products, maybe my inner product is only equivalent but not identical. So that means I cannot have identical result with the usual orthogonality if I start with inner product. Okay, so I guess I will stop there. Thank you very much for today.